First, I wanted to say my collaborators so far on this project have been Ryan Smith, Nathan Putman, Lou Gramer, Rick Lumpkin, and Frank Mueller-Carger. And the motivation for this particular seminar and for this study was that, as I think you're all aware of, sargassum seaweed began washing up on the beaches and coastlines of the Caribbean islands, West Africa, and equatorial Brazil in 2011, and again in 2014-15. The effects on commercial and recreational fishing and tourism were severe. The seminar organization today is, as probably you know too well in my division, I'm working on a paper that explains the 2011 sargassum accumulations in the Caribbean, West Africa, and equatorial Brazil in terms of the negative phase of the North Atlantic Oscillation of winter 2009-2010. The first part of my seminar will be about this topic. It'll be a tiny bit repetitive for those who were here last year, but there's also new material and some new faces in the room, so I'll just go quickly through that. And then the second part of my seminar will be a brief description of other physical and biological consequences of the 2010 NAO anomaly on both sides of the North Atlantic that I have found in scientific articles and press reports. And that part will go a little more quickly, and it's kind of interesting how many things that we may have noticed at the time turned out to be attributed to that particular NAO. Okay, where did the unusual sargassum pileups come from, and why did this happen? Hypothesis number one is that the initial sargassum inundations in 2011 came from the Sargasso Sea, where it has always previously been found, in response to anomalous wind forcing over the North Atlantic due to the strongly negative NAO in the winter of 2009-2010. That seems pretty straightforward. You find something washing up in the beaches, you know only one place where it's been seen before. It would seem as if it would come from there, but it's actually still somewhat of a controversial point among people who've been studying this, and so it needs to be proven in the form of a paper. I think we've got wonderful evidence now. Okay, a quick review. The North Atlantic Oscillation tracks the sea level atmospheric pressure difference between the Icelandic low and the Azores high. A negative NAO in the right panel, which is the case we're talking about, causes the westerlies, the red arrows, to move farther south, and the trade winds, the black arrows, to weaken or even reverse in the case of the NAO event we're talking about, compared to a positive NAO situation in the left panel. And it has many other weather-related and climate effects that we'll be discussing. First of all, here's a time series just from 2004 through 2016 of the NAO index. The NAO reached its lowest 4-month average value. It's hard to see that, but the first red arrow is the main one I want to discuss. And although it's not the peak 1-month value that's the lowest, it was the lowest 4-month average value in the winter ever seen since records have been kept on this back to 1895. So it's a big event and a prolonged event in NAO circles. Then you'll also notice that there was a recurrence of it at the end of 2010 when winter began again in December, and one more pretty extreme event in March 2013. So what were the winds like during the negative NAO event compared to climatology? We can answer this question using monthly wind data from the NSEP reanalysis that many people around here have used successfully. I used monthly data, and it gives you winds and currents and things. So pretty realistically compared to any other product that you want to compare it to. We're talking about such a big signal in this case that I feel very comfortable using almost any product for this. All right, the climatological January, February, March winds in meters per second from 2008 to 2015 are shown in the upper panel. Note the weak winds within and to the east of the Sargasso Sea, shown as the black oval. I got that from the Sargasso Sea Commission's reports. So it's just a nominal location, so when I say Sargasso Sea, that's going to be where we're talking. Winds from January, February, March 2010 are shown in the lower panel. The strong southward shifted westerlies, the red vectors between 30 and 40 north, now extend to east of 20 degrees west. And you can see it's quite a dramatic difference from the climatology. And then even more so in March, just to show you another example of these are kind of quasi-repeatable traits of the NAO. The climatology is shown in the upper panel. The winds from March 2013 during the wind anomaly are shown in the lower panel. And you can see this wind anomaly is even stronger than that of 2010 and extends across the entire Atlantic between 20 and 40 north, from 80 west to the Mediterranean Sea. And I gave you a little rectangular box there because the next slide will do an average time series of the winds in that box. All right, here are the U winds, the zonal or east-west component of the winds, with positive being to the east from NCEP, averaged over that box and made into a time series from 2008 through 2016. The climatology is red, the monthly values are blue, and the anomaly values are green. And note the reversal of the normally westward trade winds during early 2010, late 2010, and March 2013. That's a really big change. The trade winds in that area almost always blow towards the west, and that year they reversed. And so I think all the various fishermen and sailors and people in Miami paid attention to that during those winters. And that's why it was. Now, what can we learn from satellite-tracked surface drifter data? Both surface drifters and floating sargassum will be subject to a certain amount of windage, which is direct wind forcing at the surface of the ocean in the direction of the wind. Its effect varies depending on the shape of the floating object and how deeply it extends into the water column. Surface drifters that have lost their drogues are likely to behave very much like floating sargassum, at least the floating sargassum at the surface. As sargassum ages, it can sink and things, but there's many papers and things that show that sargassum, for example, during hurricanes, blows straight in the direction of the wind up onto shore in an unusual way. We know that sargassum does respond to at the very surface to the direct wind forcing, as well as to the prevailing currents. So we'll take a look at that. This is the average number of drogue drifters, and Rick in the Drifter Center were kind enough to share this data with me. The average number of drogue drifters in 5-degree boxes between 2008 and 2015. It shows that the North Atlantic subtropical gyre, due to the convergent Ekman transport, which is southward north of about 30 and northward south of 30 in the Sargasso Sea area, tends to aggregate drifting objects between about 20 and 50 north. These are the drogued drifters, so they're going like the currents in the drogues, I think, are centered at 15 meters, so it's taking a big chunk of the upper layer flow. This, however, is the same thing for undrogued drifters. Only the portions of the drifter trajectories that lost their drogue already show that the influence of windage tightens up the convergence zone or garbage patch located within the North Atlantic subtropical gyre. This agrees much better with observations of sargassum and marine debris than the previous one did. Floating, and you'll see more later, floating objects in the Sargasso Sea are generally constrained to stay there. Now we're going to look at the January, February, March comparison of undrogued drifters. Here we are for the climatological January, February, March picture. It's similar to the previous slide for all the months of the year, with tight constraint in the subtropical gyre. Note that the implied sharp southward turn along the east side of the gyre occurs at around 20 west, just for your reference for the next figure. This is the same analysis, but for January, February, March 2010, it's quite a bit different in a couple of important ways from the climatological January, February, March. The NAO-induced eastward wind anomaly disrupted the climatological pattern and blew the undrogued drifters rapidly to the east, all the way to Gibraltar at about 8 west. Some also seem to have escaped the gyre to the north and to the south. Now, one little slide about windage. What is windage and why is it important to this story? The reason undrogued drifters behave differently from drogued drifters is windage. Much evidence in the literature shows that sargassum and other marine debris or flotsam often blows ashore during storms and other extreme wind events. Empirical studies have shown how important windage is to the movement of various types of objects at the surface of the ocean. Typically, adding a windage factor of 1 to 3% of the wind speed in the direction of the wind best matches the observations. Recent HICOM modeling studies by Lou, yes, in the back, that we worked together on this, have shown that without windage, even the average distribution of sargassum, as well as we saw with the undrogued drifters, is not explained, much less its dramatic behavior during anomalous winds. He also looks very closely at Stommel shear, which is related to windage, but has a different angle, and it's a similar concept. And so it makes a lot of sense that if you tweak that windage or Stommel shear numbers correctly, you should be able to recreate both the mean picture of floating things like sargassum and the anomalous behavior. All right, this map shows the climatological NSEP January, February, March surface currents, not wind, surface currents, with a 3% windage factor applied as described in the previous slide. Note the zero currents, this is the climatology here, the zero currents in the center of the Sargasso Sea, just where you would expect, bracketed by eastward currents with a slight northward component to the north and westward currents to the south. Importantly, note that the flow near Gibraltar and along the African coast appears to come from north of 40 north. If you follow the vectors just qualitatively, you can see that it's coming from north of the 20 to 40 band for the most part. And then it continues down south all the way down to about 15 degrees or so and splits into the well-known African part and tropical Atlantic part, and those are strongly seasonally reversing currents there that have been well studied. Now we have, during the anomaly, shows the NSEP surface currents with the same 3% windage factor applied. The currents in the Sargasso Sea are nearly all directed towards the east, extending to Gibraltar before turning south along the coast of Africa. Now the southward coastal flow comes directly from the Sargasso Sea, even from the central Sargasso Sea, basically the entire Sargasso Sea, and not from the north, providing a pathway for sargassum into the tropics. And this will explain some of the other physical and biological consequences I'll talk about in the second part of the talk. Now this is new for everybody. Sargassum data from the sea semester program. Direct observations of sargassum using Houston net tows in the North Atlantic and Caribbean Sea over many years, kindly shared with us by the sea semester program, which is run out of Woods Hole, is on a sailboat for undergraduates, can provide ground truthing for all of these ideas. The data used in the analysis shown in the next two slides were collected between 2006 and 2016 in the Sargasso Sea and the Caribbean Sea. Only the two particular species of sargassum historically found in the Sargasso Sea, Sargassum natans 1 and Sargassum fluitans 3, were considered in this analysis for reasons that will become clear, and I will now call those two types specifically total sargassum. It's the type you've always known to be found in the Sargasso Sea. Cruise averages of total sargassum calculated within lat-long boxes in the Sargasso Sea, the red box, and the Caribbean Sea, the green box, were used to produce time series. A total of 27 cruises in the Sargasso Sea and 31 cruises in the Caribbean were used in the analysis. If anyone has a burning question at some point, I didn't make something clear, you can go ahead and interrupt me. All right, these are the total of those two specific species of sargassum. Sargassum time series in grams per square meter over approximately 2,000 meter long surface net tows show that sargassum levels were abundant in the Sargassum Sea, the upper panel, prior to both NAO wind anomalies in 2010 and 2013. Although with all biological quantities, there's quite a bit of noise still, but each of the dots on there is one cruise averaged in one box. But they dropped sharply after each anomaly, particularly right after December 2009. It went all the way down to 0 by the end of the anomaly. And then it kind of built up with some noise, but then crashed again right after the March 2013 anomaly. Now this is what gets really interesting. However, in the Caribbean, the lower panel, sargassum levels spiked in 2011 and 2012 after the first wind anomaly, but did not show a second spike in 2014, 2015. The reason for the delay of the arrival in the Caribbean was that just happens to be, we can tell by the NSEP data and by the drifter trajectories, not shown that that's about how long it took for it to get over there by the pathway that I laid out for you. So that is pretty interesting proof that it was rarely seen in the Caribbean before the 2011, 2012. That's why it was such an astonishing thing to everyone, never been seen before, made all the press, ruined the tourism, everything. And it's kind of obvious how that happened. So a mystery remains. We could show that the 2011 sargassum inundations in the Caribbean came from the Sargasso Sea, but where did the sargassum that piled up in the Caribbean in 2014 and 2015 come from? Clearly not from the Sargasso Sea, as levels there remained low then through 2016. The answer to this mystery also lies in the sea semester data. In a presentation last year at GCFI in Grand Cayman Island and a recent paper in Oceanography with the reference down below, the sea semester PIs showed that a different species of sargassum, natans 8, had bloomed in the tropical Atlantic in great quantities in 2014 and entered the Caribbean with the prevailing currents. However, the reasons for this unusual bloom in the tropical Atlantic are still unknown, and they're the subject of much scrutiny and scientific analysis and satellite studies and all kinds of things. But the sea semester people assure me that there is not a chance that even if the sargassum from the Sargasso Sea got into a nutrient-rich, warmer environment with iron, dust from, nothing would make it morph into, they are convinced, and they've done DNA studies too, that indicate that yes, it is definitely a different kind. And then I asked them, well, if there were small quantities of the sargassum 8 times 8 and in the Sargasso Sea, and if those small quantities got into the high nutrients and everything, they said that's a possibility that they will be looking into, So either it spontaneously erupted, that species, or it came in from somewhere and found itself in an entirely different environment. But the reasons are, to this moment, still unknown.
And then
yes.
Where exactly are you talking about in the tropical Atlantic?
Oh, I'm talking about in the kind of area offshore of Barbados. They're a large area where Xuan Min, who sees his accumulations and everything, and they're beginning to talk down there about, you'll see in a minute, but why I don't think this is probably it, but that it's accumulating. There's a new blooming area and going to stay blooming there, but I think for physical reasons, that's going to be unlikely. We'll see, though. Time will certainly tell. So that's the type that's piling up on the beaches recently. I think 2016 and 17 were lighter years, however, for sargassum. Whoops. Oh, it still works. I hit the down button instead of the right button. Will the sargassum accumulations continue to occur? Is this the new normal? That was everyone's fears at first when this was happening. And hypothesis number 2 is that the pelagic sargassum accumulations in the equatorial Atlantic will eventually be self-limiting due to the divergent nature of the large-scale winds and currents in the tropical equatorial North Atlantic. So this is just a schematic of the large-scale surface currents. The next 2 slides will illustrate the effect that these currents would have on sargassum and other floating objects. Note the location of the red star at about 16 north, 20 west in the southward current along the west coast, along the coast of West Africa. We have absolutely, from the NCEP reanalysis data with Windage and drifter trajectories themselves, absolutely can show that things can get down as far south as 16 north along the coast of Africa there. At that point, there's a gyre that sometimes diverts things offshore, and there's question, but we know that if that star can be connected to the whole tropical circulation. Now I'm going to show you a little bit of data from the Adrift website. Eric Van Sabil's reference on this is down at the bottom if you're interested. The Adrift website uses the entire drogued plus undrogued global drifter data set back to the 70s to determine statistically where surface drifters would end up 0 to 10 years after deployment at a specified initial location. While individual anomalous years such as 2010 cannot be separated out using this analysis, by including both the drogued and undrogued drifters, the effect of windage is included, and therefore the results should be relevant to the movement of sargassum. Okay, these 4 maps, I hope that they're big enough to see. You can just, from the colors, kind of tell what's happening. I've shown year 1, year 2, year 4, and year 10 after an initial deployment at the red star over there at the location that I said. Note the rapid but temporary spread to tropical West Africa almost right away. I mean, you could see it reaching the tropics and going in both directions with the zonal currents down there. Brazil by year 2 and the Caribbean. As a matter of fact, even by year 4, the whole area is full of sargassum. However, by year 10, if you keep this running, you'll see the eventual accumulation in the Sargasso Sea and a small but intriguing area off of West Africa. So for the most part, that looks just like, as it should, probably the pictures we saw of the undrogued drifter statistics. But this just shows, you can see all the years too. It's really fascinating to use this website and take a peek at it this way. But so we can see exactly what would happen once we got our sargassum down to that red star. And the small area off West Africa is intriguing, possibly, I don't know, in the case of the other type of sargassum, there may be a story there of some sort where you can have an accumulation region that can bloom and then be interconnected with the other areas.
Libby, how long does a real drifter last?
A real drifter lasts, oh, some of them, we had one we deployed on one of our cruises that lasted like 5 years and went over to Europe from the Caribbean. But in general, I would say drogued plus undrogued phases might be up to 3 years. Is that true, Rick?
That's true, but can you go back again to that?
Yes.
Because that area off Africa is a death zone for drifters. It's an area where they live a few weeks.
But there's still,
something curious.
Yes, I think there's something very interesting there. That's only from the drift. You know, he just takes statistics of where drifters have gone from one.
I think he normalizes it in such a way that if things might get really weird if the drifters are dying very quickly because he doesn't allow the tracer to die.
Right.
Because it's conserved.
Right, that's true.
So I think that might be hard.
And I did do a little study, I'm not showing it in here, of all the places where drifters run ashore and die and everything, and that makes. But we do need some kind of something has to explain why we can be having the other kind pluming and where it could have come from. It hasn't been shown in the South Atlantic or anything. This may not be it for those reasons that you say, but the main point I wanted to make is this is why going from year 2 to 4 to 10, why I don't believe that pelagic sargassum, which has no roots, whatever kind it is going to be able to really last long. It'll go back and forth maybe a couple of times, and then all roads lead to the Caribbean and out again. So we'll see. Time will tell if it was an isolated event.
And while we're here also, I want to mention that I can provide to you this calculation, but for undrogued only and for unconserved, so it'll die.
That would be wonderful. Yeah, I just hadn't wanted to bother you until I had like a draft to hand onto your desk neatly. But it's coming along. So, all right. That's the first part. We're right on schedule. Don't worry. Summary and conclusions of Part 1, Sargassum. There were unprecedented accumulations of sargassum on the beaches of the Caribbean Sea during 2011, 2014, and 2015. The 2011 event was likely related to anomalous eastward winds triggered by the record lows in the NAO during winter 2009-2010 that caused the sargassum to drift rapidly to the east, after which it would have drifted into the tropical Atlantic, coastal Brazil, and Caribbean with the prevailing seasonal trade. Can you still hear me? I don't know where it went. I think it was. It's okay? Okay. With the prevailing seasonal trade winds and currents. Hypothesis number 1, that the 2011 sargassum event originated in the Sargasso Sea, is supported by data from the NCEP reanalysis model and the Global Drifter Program, as well as sea semester net tow data. However, the 2014 and 2015 events likely had another cause. Hypothesis number 2, that the sargassum inundations will be self-limiting due to the divergent nature of the winds and currents in the tropical North Atlantic Ocean, remains to be proven with time. However, the Adrift analysis suggests that this will be the case. I don't think that's me. Okay. Other physical and biological consequences of the 2009-2010 negative NAO. I think this is going to be the fun part for you guys, because as I started kind of looking into this, well, heck, you know, if it moved sargassum around in such a large scale way, sort of, what were some of the other things that were also happening then? And I found some incredibly interesting ones. So we'll just go briefly through them, a few photographs and some references for you. The negative NAO caused a large-scale change in the wind patterns over the North Atlantic, which included weakening the normally easterly trade winds. This effect was so strong that it caused an anomaly in the Atlantic meridional overturning circulation, which many people here are well aware of and have been monitoring since 2004. Just briefly to show you, this is the transport of the AMOC at 26.5 north in purple is comprised of the sum of the transports of the northward Florida current in blue at the top, a southward geostrophic term, green, and a usually northward Ekman transport term in red. Note the NAO-induced reversals of the Ekman transport in early and late 2010 and again in March 2013, which appear to be driving the very low AMOC transport events during the same time periods. And I believe that there's thought perhaps to be some feedback. It's not clear apparently which causes which to happen, but it's clearly associated with it. And probably, I think I read a recent paper that showed in the short term, the response to the winds is very rapid, right, of the transport. I think you want to post that. Okay, so in this particular case, we think it was the wind anomaly from the NAO that caused the drops in the AMOC.
But what they call that double dip in the winter of 2010, 2011 is the controversial one, where some people.
That's the recurrent.
The fact that it's delayed.
Nobody can hear the other half of this conversation.
Okay, sorry. We will if it's. I'll remind it as a question at the end. We have a mic for that. Sorry. Okay, I know. The reemergence one, the December 2010 NAO, low NAO, is called reemergence. It's thought to be related to the fact that over the summer after the first one, warm temperatures capped off the North Atlantic, but that all it took was a little prompting when the next winter came along to suddenly have another big one again, because all that cold water was just under the surface. But it may have been, what Bill was saying was that it may have been that it was the AMOC itself that helped trigger the next one to happen, given that the cold water was there. That's a subject of great research right now, people are doing. But it's clear that the NAO modified something as huge and important climate-wise as the AMOC there. So there's many other things, too, that happen. Next, we'll look at several other large-scale effects of the winter negative NAO anomaly. We will begin with the U.S. East Coast and Western Europe, both of which experienced unprecedented and cold temperatures and severe snowstorms. You can see we're in this graphic, the same one we were looking at winds before. Now we're looking at the cold coming down from the far north in both of those areas due to the negative phase of the NAO. This is from a little paper in Weatherwise. This is snow in Pittsburgh during the first North American blizzard of 2010. And I actually went up to Boston to visit my dad in January of 2010, and I grew up in New England. I've never seen Boston like that. The snowdrifts at the edges of all the roads were 10 feet high. They were dumping it into the bay, and they were trying to get rid of it any way they could. Never saw anything like that, and I lived there all my life. So that's a pretty cool picture of it. Closer to home, the 2010 cold event caused severe mortality to corals of the Florida Reef Tract. This is from a paper by Diego Learman et al., and some people here in this building were co-authors of that in +1. In response to the cold northerly winds along the U.S. East Coast caused by the NAO, the coastal waters of South Florida, including Biscayne Bay, Florida Bay, and the Florida Keys National Marine Sanctuary, reached temperatures lower than 10 degrees C or 50 degrees F. Water temperatures are shown here as time series for Biscayne Bay in the upper, middle, and lower Keys during the month of January 2010. The cold water event lasted for most of the month, with the most harmful, lowest temperatures present for a week to 10 days. The effect on the coral reefs was devastating. This was the worst cold water mortality event, I believe, that had ever been recorded in the Keys.
The worst mortality event, period.
Oh, really? Oh, that's interesting. Okay. And in Western Europe, I like that picture there. I can't say for sure that that's in January or February 2010, but I liked it as a castle in Europe. But these were during the event I'm talking about. Cold swans in France and one poor cold doggy in England. So was no better in terms of low temperatures and severe snowstorms. Here's the snow cover from AccuWeather as of February 16th. Shows that nearly all of Europe north of the Mediterranean Sea and east of France was covered by over a foot of snow at the same time. That was really quite phenomenal. And this map from Wikipedia of Europe shows the difference of temperature between December 11th to 18th, 2009, at the beginning month of the cold anomaly, and the December average for 2000 to 2008. As you can see from the colors, the temperature anomalies reach as low as 15 to 20 degrees C in places. Really quite astonishing. Other consequences of the cold temperatures and heavy snowfall in Western Europe included many deaths of livestock, particularly sheep, and humans, and disruption of services such as electricity and transportation. Closer to the Atlantic coast, Spain, Portugal, France, and the Madeira and Canary Islands experienced unprecedented flooding from a series of storms that came from the west as part of that wind event. This flooding caused many deaths and destruction to buildings and roadways, and a large rockfall from Gibraltar fell into the sea. I mean, I could look up this. A really big event crashed down into the adjacent waters. And in addition, the sea level rose in the Mediterranean Sea by 12 centimeters as a direct result of the eastward wind anomaly caused by the negative NAO. And the reference for this from 2013 is at the bottom. And Dennis is also working on some interesting further studies on this phenomenon. But this is a case of, they believe that the water just blew directly into the Mediterranean in a way it does not normally do due to the strong eastward sustained winds. And I would say that's a rather amazingly big sea level rise due to that, due to wind over the whole Med and the Adriatic, by the way. Finally, two of the more interesting biological consequences of the negative NAO, besides the sargassum in the Caribbean, involve the large-scale relocation of several species of marine life to regions outside of their normal distributions. So there are two more of these. In the Caribbean, ecotour leaders noted the presence during 2011 of marine species of fish, crabs, baby turtles, and baby European eels that are usually associated with the rafts of sargassum seaweed in the Sargasso Sea. They're over the long term adapted. They look like sargassum. They're endemic, I think that's the word, to sargassum, and it's a whole community. These life forms had likely been blown out of the Sargasso Sea with the sargassum and ended up in the Caribbean Sea where they had not previously been seen before. This blog from one leading ecotourism person showed photographs of the eels and talked about where they had seen them and all. And they were associated with ongoing rafting of sargassum at the time. So it's so those had never seen the Caribbean before. I suppose the conditions were good for them. I don't know what happened after that. My theory would be that they traveled on up into the Gulf and Florida Current and back home again into the Sargasso Sea. And finally, this is the coolest one of all, I do believe. One of the most bizarre consequences of the winter 2010 negative NAO ruined the beach tourist season in the Mediterranean Sea the following summer in July, August 2010. And I didn't hear about that at the time, when there was a massive invasion of Phasalia, or Portuguese man-of-war, that blew ashore from the North Atlantic during the same big wind event that transported the sargassum to the east. Now these would tend to have even more windage. These are like a balloon with tentacles. Every object, all the studies have shown, it depends on the shape and the windage, the weight and size and characteristics of the object that's blowing. These float right on the surface and have their poisonous tentacles down below. This is from a paper by Prieto et al. About Portuguese man-of-war in the Mediterranean. At the top, you see the number of Phasalia sightings on the coasts of the Mediterranean Sea, the Iberian Peninsula, and Canary Islands are shown during we're talking about the time series up in the upper right corner. The levels normally are around 20 to 40 sightings, and it increased to more than 800 during 2010, which is a pretty dramatic difference. And the monthly climatology from 1979 to 2012 of the U component of the wind in the Atlantic Ocean from a different product. I didn't write down which one that is, but it's entirely separate from the NSEP. So they computed the winds in that rectangle, the red rectangle. And you can see the black line is the climatology, and the red dots and red line are the actual winds for the November through March period. And they run modeling studies also and show that pseudoparticles would have done exactly that. This is very unusual because, as I believe, they still have yet to have a drifter, drogued or undrogued, go through Gibraltar. Is that true, Red? You know, I read that somewhere on somebody's. Okay, but I looked for I searched that box closely and could find no evidence of a drifter going into the Med ever. But so that's actually pretty cool. Let's see. If I'm not going to say it later in the summary, I did want to point out that several medical papers were also written about the Portuguese man-of-war event. They collected data from emergency rooms and health care centers and things. There were numerous, hundreds of people who had to go to the emergency room with stings, and one woman died, the first death to Portuguese man-of-war ever in the Mediterranean. So summary and conclusions, part 2. Other consequences. The record-breaking negative phase of the North Atlantic Oscillation caused many physical and biological consequences in the North Atlantic Ocean and surrounding land areas. Some of the physical effects were an increase in the strength and displacement to the south of the westerlies and a reduction or a reversal of the trade winds in the subtropics and tropics. This change in the normal wind pattern caused extremes in cold temperatures and precipitation in the form of either snow or flooding rains in the eastern U.S. and western Europe. It also caused Atlantic water to flow directly into the Mediterranean Sea, raising its sea level by 12 centimeters. In addition, the anomaly in the trade winds caused the transport of the Atlantic meridional overturning circulation at 26.5 north to reach its lowest values since measurements began in 2004. Some of the biological effects included sargassum inundations of the Caribbean Sea, Western Africa, and Equatorial Brazil, as well as loss of human and animal life due to the cold, snow, and flooding. The winter 2010 NAO is also responsible for the first major Portuguese man-of-war invasion of the Mediterranean beaches. Here we are, causing numerous emergency room visits and at least one death. This is the final thought. These events, all traceable to a single large-scale climate anomaly, suggest that in a future changing climate, the interaction of physical forcing, both meteorological and oceanographic, and land and sea-based biological ecosystems may produce a variety of unexpected consequences. Thank you.